Hello, I'm Robert Miles. Welcome to this recording of the Alignment Newsletter podcast. This is newsletter number 96. Buck and I discuss/argue about AI alignment. Published on the 22nd of April 2020 by Rohans. Highlights. Link AI Alignment Podcast, an overview of technical AI alignment in 2018 and 2019, with Lucas Perry, Buck Schlageris, and Rohans. Summarized by Rohan. This podcast with Buck and me is loosely structured around the review I wrote, which was newsletter 84, but with a lot more debate and delving into specific points of pessimism and optimism. I suspect that every reader will have some section they're interested in. Since much of the discussion was itself meant to be a summary, I'm not going to try to summarize even further. Here's the list of topics covered. Our optimism and pessimism about different approaches to aligned AI, traditional arguments for AI as an X-risk, modeling agents as expected utility maximizers, ambitious value learning and specification learning/narrow value learning, agency and optimization, robustness, scaling to superhuman abilities, universality, impact regularization, causal models, oracles and decision theory, discontinuous and continuous takeoff scenarios, probability of AI-induced existential risk, timelines for AGI, and information hazards. Section Technical AI Alignment. Subsection Technical Agendas and Prioritization. Link AI Services as a Research Paradigm by Vojta Kovarek, summarized by Rohan. The CAIS report, discussed in newsletter 40, suggests that future technological development will be driven by systems of AI services rather than a single monolithic AGI agent. However, there's not been much follow-up research since the publication of the report. This document posits that this is because the concepts of tasks and services introduced in the report are not amenable to formalization, and so it's hard to do research with them. So, it provides a simple abstract model of a system of services in which each service takes some inputs, produces some outputs, and is trained with some loss function, and these services are interconnected with each other. Some of the services could be provided by humans instead of AI systems. It then lists several research problems that could be tackled under this generic view. Rohans Opinion. I was expecting a list of questions that were specific to AI somehow, but the actual list is very broad and feels to me like a list of sub-questions of how do you design a good society in the face of technological development. For example, it includes unemployment, system maintenance, the potential of blackmail, side-channel attacks, etc. Subsection Learning Human Intent. Link Aligning AI to Human Values Means Picking the Right Metrics by Jonathan Stray, summarized by Rohan. There's been a lot of attention recently on the flaws of recommender systems, especially when optimizing for simple metrics like engagement, an example of what we might call narrow value alignment. This post reconstructs how Facebook and YouTube have been incorporating better metrics into their algorithms from 2015 and 2017 respectively. For example, Facebook found that academic research suggested that well-being was improved by meaningful social interactions, but worsened by passive consumption of content. As a result, they changed the metric for the recommendation algorithm to better track this. How did they measure it? It seems that they simply asked a survey of thousands of people what the most meaningful content was, both on and off Facebook, and used this to train a model to predict meaningful interactions. They estimated that this resulted in a 5% decrease in time spent on Facebook, at least in the short term. The story with YouTube is similar, though sparser on details, and it's not clear if there was input from end users in YouTube's case. The author then contrasts this sort of narrow value alignment with AGI alignment. His main take is that narrow alignment should be easier to address, since we can learn from how existing systems behave in the real world, and the insights we gain may be critical for AGI alignment. I'll end with a quote from the conclusion. My argument is not so much that one should use AI to optimize for well-being. Rather, we live in a world where large-scale optimization is already happening. We can choose not to evaluate or adjust these systems, but there's little reason to imagine that ignorance and inaction would be better. Rohans Opinion. Even though I often feel like an optimist about incentives towards alignment, as discussed in newsletter 80, even I was surprised to see the amount of effort that it seems Facebook has put into trying to align its recommendation algorithm with well-being. To the extent that the recommendation algorithm is still primarily harmful, which might be true or false, I don't know, this suggests to me that it might just be really hard to give good recommendations given the sparse feedback you get. Of course, there are more cynical explanations. For example, Facebook just wants to look like they care about well-being, but if they really cared, they could do way better. I lean towards the first explanation, but it's very hard to distinguish between these hypotheses. While the post claimed that narrow value alignment should be easier than AGI alignment, I'm actually not so sure. With AGI alignment, you have the really powerful assumption that the AI system you're trying to align is intelligent. This could plausibly help a lot. For example, maybe the recommender systems that Facebook is using are just incapable of predicting what will and won't improve human well-being, in which case narrow alignment is doomed. This wouldn't be the case with an AGI, depending on your definition of AGI. It should be capable of doing at least as well as humans do. The challenge is in ensuring that the AI systems are actually motivated to do so, as discussed in Newsletter 33, not whether they're capable of doing so. With narrow alignment, you need to solve both problems. Link: Less is More, Rethinking Probabilistic Models of Human Behavior, by Andrea Bobu, Dexter R.R. Scobie et al., summarized by Asya. This paper introduces a new model for robots inferring human preferences called LESS, less. The traditional Boltzmann noisy rational model assumes people approximately optimize the reward function and choose trajectories in proportion to their exponentiated reward. The Boltzmann model works well when modeling decisions among different discrete options, but runs into problems when modeling human trajectories in a continuous space, for example pathfinding, because it's very sensitive to the number of trajectories, even if they're similar. If a robot using a Boltzmann model must predict whether a human navigates around an obstacle by taking one path on the left or one of three very similar paths on the right, it will assign the same probability to each path by default. To fix this, LESS predicts human behavior by treating each trajectory as part of a continuous space and mapping each one to a feature vector. The likelihood of selecting a trajectory is inversely proportional to its feature space similarity with other trajectories, meaning similar trajectories are appropriately de-weighted. The paper tests the predictive performance of LESS versus Boltzmann in several experimental environments, including an artificially constructed task where humans are asked to choose between similar paths for navigating around an obstacle, and a real-world task where humans demonstrate appropriate behaviors to a 7-degree of freedom robotic arm. In general, LESS performs better than Boltzmann when given a small number of samples of human behavior, but does equally well as the sample size is increased. In the robotic arm task, Boltzmann performed better when demonstrations were aggregated into a single batch and inference was run on the whole batch at once, representing trying to approximate the average user rather than customizing behavior to each user. The paper claims that this happens because Boltzmann overlearns from demonstrations in sparse regions and underlearns from dense demonstrations. As you increase the number of samples, you approximate the true trajectory space better and better, so the 10 trajectory sets vary less and less, which means Boltzmann won't underperform so much. Since the single batch demonstration aggregated demonstrations, it had a similar effect in approximating the true trajectory space. The paper notes that one limitation of this method is a reliance on a pre-specified set of robot features, though a small set of experimental results suggested that LESS still performed better than Boltzmann when adding a small number of irrelevant features. Asya's opinion. This seems like a good paper, and seems very much like the natural extension of Boltzmann models to include accounting for similar trajectories. As the paper notes, I largely worry about the reliance on a pre-specified set of robot features. In more complicated cases of inference, it could be impractical to hand-specify relevant features, and too difficult to have the robot infer them. In the worst case, it seems like misspecified features could make performance worse than Boltzmann via suggesting similarities that are irrelevant. Rohans Opinion. Note that this paper comes from the Interact lab, which I'm part of. The Boltzmann model of human behavior has several theoretical justifications. It's the maximum entropy, i.e. minimum encoded information, distribution over trajectories, subject to the constraint that the feature expectations match those of the observed human behavior. It's the maximum entropy distribution under the assumption that humans satisfies her expected reward above some threshold, etc. I've never found these very compelling, and instead see it as something far simpler. You want your model to encode the fact that humans are more likely to take good actions than bad actions, and you want your model to assign non-zero probability to all trajectories. The Boltzmann model is the simplest model that meets these criteria. You could imagine removing the exponential in the model as even simpler, but this is equivalent to a monotonic transformation of the reward function. I view this paper as proposing a model that meets my two criteria before, and adds in a third one. When we can cluster trajectories based on similarity, then we should view the human as choosing between clusters rather than choosing between trajectories. Given a good similarity metric, this seems like a much better model of human behavior. If I'm walking and there's a tree in my path, I'll choose which side of the tree to go around, but I'm not going to put much thought into exactly where my footsteps will fall. I found the claim that Boltzmann overlearns in sparse areas to be unintuitive, and so I delved into it deeper in this comment, and there's a link to a comment on the alignment forum. My overall takeaway was that the claim will often hold in practice, but isn't guaranteed. Subsection Preventing Bad Behavior. Link Curiosity Killed the Cat and the Asymptotically Optimal Agent by Michael Cohen et al. Summarized by Rohan. In environments without resets, an asymptotically optimal agent is one that eventually acts optimally. It might be the case that the agent first hobbles itself in a decidedly suboptimal way, but eventually it will be rolling out the optimal policy given its current hobbled position. This paper points out that such agents must explore a lot. After all, it's always possible that the very next time step will be the one where chopping off your arm gives you maximal reward forever. How do you know that's not the case? Since it must explore so much, it's extremely likely that it will fall into a trap where it can no longer get high reward. For example, maybe its actuators are destroyed. More formally, the paper proves that when an asymptotically optimal agent acts for any event, either that event occurs, or after some finite time there's no recognizable opportunity to cause the event to happen, even with low probability. Applying this to the event the agent is destroyed, we can see that either the agent is eventually destroyed, or it becomes physically impossible for the agent to be destroyed even by itself. Given that the latter seems rather unlikely, we would expect that eventually the agent is destroyed. The authors suggest that safe exploration is not a well-defined problem, since you never know what's going to happen when you explore, and they propose that instead agents should have their exploration guided by a mentor or parent, as discussed in Newsletter 53. See also Delegative RL from Newsletter 57, Avoiding Catastrophes via Human Intervention, and Shielding for more examples. Rohans Opinion. In my opinion on Safety Gym in Newsletter 76, I mentioned how a zero violations constraint for safe exploration would require a mentor or parent that already satisfied the constraint. So in that sense, I agree with this paper, which is simply making that statement more formal and precise. Nonetheless, I think there's a meaningful notion of exploration that can be done safely. Once you've learned a good model that you have reasonable confidence in, you can find areas of the model in which you're uncertain, but you're at least confident that it won't have permanent negative repercussions, and you can explore there. For example, I often explore what foods I like, where I'm uncertain of how much I will like the food, but I'm quite confident that the food will not poison and kill me. However, this notion of exploration is quite different from the notion of exploration typically used in RL, and might better be called model-based exploration, or something like that. Subsection Miscellaneous. Link Bayesian Evolving to Extinction by Abram Dembski, summarized by Rohan. Consider a Bayesian learner that updates the weights of various hypotheses using Bayes' rule. If the hypotheses can influence future events and predictions, for example, maybe it can write out logs which influence what questions are asked in the future, then hypotheses that affect the future in a way that only they can predict will be selected for by Bayes' rule, rather than hypotheses that straightforwardly predict the future without trying to influence it. In some sense, this is myopic behavior on the part of Bayesian updating. Bayes' rule only optimizes per hypothesis, without taking into account the effect on overall future accuracy. This phenomenon could also apply to neural nets if the lottery ticket hypothesis, discussed in Recon number 4, holds. In this case, each ticket can be thought of as a competing hypothesis. Section AI Strategy and Policy. Link Skynet Revisited, The Dangerous Allure of Nuclear Command Automation by Michael T. Clare, summarized by Rohan, with a hat tip to John Rodriguez. While I won't summarize this article in full here, I found it useful to see how some academics are thinking about the risks of automation in the military, as well as to get a picture of what current automation efforts actually look like. One quote I found particularly interesting. Quote, "You will find no stronger proponent of integration of AI capabilities writ large into the Department of Defense," said Lieutenant General Jack Shanahan, director of the Joint Artificial Intelligence Center, JIAC, at a September 2019 conference at Georgetown University. "But there's one area where I pause, and it has to do with nuclear command and control." End quote. Referring to an article's assertion that an automated US nuclear launch ability is needed, he said, quote, "I read that, and my immediate answer is, no, we do not." End quote. Link AI Alignment Podcast on Lethal Autonomous Weapons with Lucas Perry and Paul Shah, summarized by Flo. Paul Shah, author of Army of None, Autonomous Weapons and the Future of War, talks about various issues around lethal autonomous weapons, laws, including the difficulty of talking about an arms race around autonomous weapons when different people mean different things by arms race and autonomy comes in varying degrees, the military's need for reliability in the context of AI systems' lack of robustness to distributional shift and adversarial attacks, whether the law of war correctly deals with laws, as well as the merits and problems of having a human in the loop. While autonomous weapons are unlikely to directly contribute to existential risk, efforts to establish limits on them could be valuable by creating networks and preparing institutions for collaboration and cooperation around future AI issues. Section Other Progress in AI. Subsection Deep Learning. Link Fast and Easy Infinitely Wide Networks with Neural Tangents by Roman Novak, Leiqiao Zhao, Samuel S. Schoenholtz et al. Summarized by Zach. The success of deep learning has led researchers to explore why they're such effective function approximators. One key insight is that increasing the width of the network layers makes it easier to understand. More precisely, as the width is sent to infinity, the network's learning dynamics can be approximated with a Taylor expansion and becomes a kernel problem. This kernel has an exact form in the limit and is referred to as the neural tangent kernel, NTK. Ultimately, this allows us to model the network with a simpler model known as a Gaussian process. Unfortunately, showing this analytically is difficult, and creating efficient implementations is cumbersome. The authors address this problem with neural tangents, a library that makes creating infinite-width networks as easy as creating their finite counterparts with libraries such as PyTorch or TensorFlow. They include support for convolutions with full padding, residual connections, feed-forward networks, and support for a variety of activation functions. Additionally, there is out-of-the-box support for CPU, GPU, and TPU. Moreover, uncertainty comparisons with finite ensembles are possible via exact Bayesian inference. Zach's opinion. I took a look at the repository and found there to be ample documentation available, making it easy for me to try training my own infinite-width network. The authors derive a practical way to compute the exact convolutional NTK, which I find impressive and seems to be the main technical contribution of this paper. While the authors note that there are some conditions necessary to enter the so-called kernel regime, in practice it seems as though you can often get away with merely large network widths. If for nothing else, I'd recommend at least perusing the notebooks they have available, or taking a look at the visualization they present of a neural network converging to a Gaussian process, which relies on a subtle application of the law of large numbers. This concludes Alignment Newsletter number 96. For more information, you can go to rohanshaw.com/alignment-newsletter, where you can find all of the previous newsletters and also a spreadsheet of all of the papers and summaries that have ever been featured. Thank you for listening.